Moving from the very hot and the very AI-based stuff to cold storage. And now you might think, why do we need cold storage, long-term storage? Very simple. Coming from Germany, we are based in Germany. Cerabyte is a company, I'm the founder. Car industries has to request for AI models to be maintained, the training state to maintain for decades, because if you train an AI for autonomous driving, you may not make sure that liability cases are covered. And this is only one of the use cases, and we will present a more general form. I have Steffen with me, Steffen Hellmold, who is representing us in the US. And now I try to keep up the time. The space we are talking about is cold, right? So 7% of all data are cold, and basically very soon are cold, after 90 days only, and we want to keep them for decades. It might be your smartphone data, it might be financial data, you want to keep governmental records, scientific data. And of course, AI is going to accelerate the demand for storage over time. So what we think, AI, autonomous driving, smartphones, all that will drive enormously the demand up to a yottabyte scale. So this is much more than we can imagine today. It's going to be an enormous burden for the environment and all for our systems. And if we think of it, well, we should improve by a factor of 100x in several dimensions. One is storage capacity, TCO, energy efficiency, of course, performance and media longevity. And if you think of the impact of AI, conventional saying was like we have the CPU, we have Moore's law, and mainstream storage media had just to keep up. This was the paradigm we had in the past. Now AI is changing everything. We have much more compute, and the regular storage and memory can't cope with that. So we think with ceramic nano memory, I'm going to explain what that is in a second, we redefine the space of cold. It's going to be a separation of the very hot storage tiers and the very cold, because basically you don't have to have all data available at your fingertips. There might be a separation. There's a new S-curve, starting with new technologies we're going to explain in a minute. Now, what is the medium itself? It's very simple. It's display glass, right? You coat it with a ceramic layer, which makes it dark, like a sunglass, and then we inscribe the information. How this works, I'm going to show you in a second. But the important thing, it's scalable, it's recyclable, and it doesn't need raw earth. Take a picture of the white papers, you can read a bit more thoroughly after the presentation. What is the principle? Very simple. It's like punch cards, but on a very tiny scale, so nanometer scale. And basically, at the moment, we use QR codes. Why? Because it's the simplest way to get to a product fast. This is not the most efficient code. We're working on much more denser codes. On the right-hand side, you see a SEM image of the structures we create. Now about the durability. You might think glass is fragile. Yes, but if it's stacked in like 150 glasses on top of each other, it's quite strong. But at the same time, you can cool it down, you can heat it up, you can put it in an acidic environment at 500 degrees. EMP, EUV radiation, doesn't matter. You see, before and after, it doesn't change. You can still read the information. The other example why this is the right way we think is the scalability. These glasses, display glasses, are produced in 350 million square meters every year for all our displays, right? And only one machine can do basically 3 billion produce media a year, which is in the range of 3 zettabyte. It's only one machine. There are other scalability opportunities. You can make the glass ever thinner, because the ceramic layer is only 10 nanometers thick, it's 100 atom layers, so there's plenty of opportunity to get this volumetric storage density small, even down to a ribbon, right? So there's ribbon glass where you can store information on both sides with this technique. To summarize, basically we have the environmental data, but we have also energy, energy-free retention, immutability. There's no media degradation in that sense, you have seen that. Consequence is no data migration, and basically it's 100% recyclable. In this video, we show you briefly the concept, how it's working. So we use digital mirror devices like we have it here in this projector. Here, these are micro mirrors, 10 microns large, and they can be flipped in a very fast manner, 10 to 40 kilohertz. And you can actually project up to 2 million at the moment with one shot. So ultra fast. We take these projections and project it through a microscope. And then we inscribe this on the surfaces. To give you an overview how that actually looks like, here is on the left-hand side what I showed you before, like this writing mechanism. The optics in the middle is a reference point, and to the right there's image sensors who do it the same, basically massive parallelization. We use 20 megapixels image sensors with 1 kilohertz. This is how we retrieve and get data. We achieved in the first instance already a raw error rate of below 2%, which can be corrected with error correction quite nicely. And basically, to understand the potential of this can be ultra fast as well. So it can store ultra dense, as you have seen, but also ultra fast compared to disks, where you have a single spot writing information, or a tape where you have several spots. The matrix is always faster, as you can see. And to summarize, we built the prototype. Happy that you could visit that in Aachen and collaborate with us on testing. It's going to come later with right read hat and several library racks. And basically, the library racks are just existing magnetic tape racks. We took a cartridge like this, but modified it to fit the glass in there. And up to 150 glasses can be stacked in this. Now I hand over to Steffen.
Thank you so much. Yes, appreciate it. So if you think that you have seen this before, you're right, you have. And this is actually a process that's leveraged from maskless lithography. The first tool and demonstrator that has been developed is in principle an adapted maskless lithography semiconductor fab tool that is fully amortized in its technology today. With that, we have the benefit that the semiconductor fab tool industry will pay for the core R&D investment to develop this technology, which gives us also very significant look ahead into the future, because what you see on the right side, an E-beam matrix mask writer may be too expensive today because it's going to cost you more than $100 million, but it's foreseeable that down the road it can be adapted for storage applications and then cost scaled. The benefits that we have with that is that we can overcome the typical challenges of optical storage, which are density and speed. We can scale the density from petabytes a rack, as you can see on the right side, to exabytes a rack, as we are scaling from laser beam matrix to particle beam matrix. With that, we can also scale the bandwidth from gigabytes to terabytes a second. To give you a reference point, we'll be up basically into several terabits or terabytes even of areal density capability, which is scaling beyond anything that we have in conventional storage today. Now, as we look into sustainability again, part of the challenge for storage today is that it would be nice to know at the inception, when a bit is created, not only what cost do we have per terabyte that we need to care about, and what capacity and the access speed, but to also know what is the retrieval interval as well as the data lifetime. There's certain data that's, you could say, born cold, like for example your birth certificate. You will always want to keep it, but you will infrequently access it. Now looking at AI, another factor that is quite interesting and to some degree scary is that the storage pyramid may be looking different in the future, as we see in all the desperate efforts to get more memory or more storage closer to the processor, right? In order to better support all the large language models in the future. So the question is for all of us to think about, how will primary storage and secondary storage look like in the age of AI? One thing is for sure is we will have to significantly cost scale the TCO of storage as we know it today. And we think that it is possible to reduce the TCO compared to where we're at today by anywhere to 75 to 95%, which can be achieved by the cost, scaling of the cost of the right read system again, using amortized semiconductor fab tool technology will help us there. By using a high volume storage media that's very inexpensive, think cents, right, per carrier, as well as having immediate longevity that doesn't force you to migrate data, but allows you to retain the media as long as you wish to retain the data. And ultimately, the ideal, of course, situation is that you will not need any energy for retaining data over time. So when we further look into the opportunities for reducing carbon footprint, there clearly are two factors to that. On the left side, you see here the emerging technology layered on top of the installed storage base as we look into the future. So that gives you a little bit of an order of magnitude of impact. On the right side, you see the newly shipped storage products where you have emerging technology being layered on top of, again, conventional storage technology. Naturally, you'll see that emerging technology will take a larger and larger share. It has to, because otherwise density, cost, and energy scaling will simply not work. To give you a flavor for that, and this is an interesting one, if you've ever done a CO2 footprint analysis on a storage device, you probably will have already realized that there are lots of freedom degrees on especially how you define the workload that may greatly impact your outcome. So there is, to the tune of almost 1% of global CO2 footprint to be saved through efforts in storage alone. So to summarize that in a snapshot, it's often talked about that we need 100x storage density and more from a scaling perspective, which is certainly true. At the same time, to make this all work and not exceed the planetary power envelope, we also need to decrease the energy consumption or increase the energy efficiency by 100x. And lastly, since IT budgets are also not increasing 100x likely, we need to think about scaling the cost down by factor 1,000. That means what costs $1 a terabyte a month today will have to cost $1 a petabyte a month in the future. Otherwise, economics will not work. So when we look into that for a call to action, I think there are three areas that we can think about that would be of interest for the global community. One is the new environmental conditions under which we store and retain data. So here we have already seen requests from hyperscalers to run the new systems through special climate chambers, varying temperature, varying humidity, and see where it breaks. So we can use ideal conditions for long-term storage. Second, the total cost of ownership analysis is very important at the storage technology or device level to have informed decisions. Typically today, you provide impact as a storage vendor to the hyperscalers of the raw data. They calculate what the TCO is and make their decisions, right? But it would be nice to have that on a global scale to have at least some benchmark comparison data. And lastly, the carbon footprint, again, emissions estimates for storage devices will be more and more important also to allow legislators to put the appropriate carbon tax on the different solutions. And again, I want to go back to the example that I've showed you earlier. If you look at storage as I/O intensive or capacity intensive, your storage footprint for CO2 may greatly vary in all of that. And that is a key point for us to think about. If you have additional questions, we'll be happy to address them. Thank you so much.
Questions for Christian and Steffen, Cerabyte. While our next speakers are getting prepared, please. So I do have a question. So this is your very first presentation at the symposium, and I believe also at the regional summit. What are you expecting from this event?
So we would expect somehow a discussion, which we don't have, but I hope this was overwhelming in the sense that it's completely new. I would be happy to present it and discuss this in more detail after the show or in one of the breaks. And secondly, I think that the next step, what we see, we would love to have engagement in the sense of like testing in our hypothesis, testing our prototype, and of course, in the end, getting the CO2 calculation somehow aligned with the activities here within OCP.